In this video, we will analyze the signal-to-noise ratio that we have at the output of a coherent receiver for different amplitude modulations. In this table, in the first column, we have the power of the modulated signals for different amplitude modulations, for the conventional AM, the double sideband, the single sideband, and the vestigial sideband modulations. In the second column, we have the expression of the signal component at the output of a coherent receiver. This is the power of this component related with the modulating signal, and in the last column we have the power of the noise component at the output of a coherent receiver. That, remember, it was equal to 1/4 of N0 times the bandwidth of the modulated signal, and the bandwidth of the modulated signal was 2 times the bandwidth of the information, B hertz, for the conventional AM, and for the double sideband it was B, the bandwidth of the modulating signal for the single sideband, and the bandwidth of the modulating signal plus the vestige for the vestigial sideband. In the calculation of the signal-to-noise ratio, we have assumed that the received signal is equal to the modulated signal plus noise. And from this table, we'll compute the signal-to-noise ratio for all these modulations, basically as the ratio between the power of the signal component and the power of the noise component that we have at the output of this receiver. And the obtained signal-to-noise ratio will be compared with a reference, and this reference is going to be the signal-to-noise ratio that we have in a baseband transmission, which is equal to the ratio between the power of the signal at the input of the receiver and N0 times the bandwidth in hertz of the information of the modulating signal, N0 times B in this case. This is going to be the reference that we are going to compare against the signal-to-noise ratio for every modulation. We start the analysis for the double sideband modulation. In this case, the signal-to-noise ratio is the ratio between the power of the signal component and the power of the noise component. In this case, if now we have this 1/2 here and 1/4, simplified, we can see that the signal-to-noise ratio can be written as follows. And what we have here in the numerator, half of the square of the carrier amplitude times the power of the modulating signal, is just equal to the power of a double sideband modulation. Therefore, we can write the signal-to-noise ratio for the double sideband as PS divided by N0 times B, which is equal to the signal-to-noise ratio that we have in a baseband transmission. The same result will be obtained for a single sideband modulation, where the power of the signal component is this one and the power of the noise component is this one. If we have this ratio, the quarter here and the quarter here cancel, and we have this expression, and now again what we have in the numerator is equal to the power of a single sideband modulation. Therefore, what we have is PS divided by N0 times B. What we have is the same result that in transmission for a baseband signal. As a conclusion, the double sideband modulation and the single sideband modulation have the same signal-to-noise ratio than in a baseband transmission. For a conventional amplitude modulation, the power of the signal term is this one and the power of the noise term is this one. If we write this ratio, we have this expression. This 4 here and this 2 here can be simplified to this expression. Now we want to write this expression as a function of the power of the modulated signal, and because of this we multiply and we divide by 1 plus the power of the modulating signal with modulation index A. And regrouping, we can see that now what we have is PS divided by N0 times B times this factor here. Therefore, what we have is something that is different right now from the signal-to-noise ratio in a baseband transmission. And the term that we have here is lower than 1 because the denominator is 1 plus the numerator. And this is the conclusion that we have for the signal-to-noise ratio in a conventional amplitude modulation. The signal-to-noise ratio is worse than the signal-to-noise ratio for a baseband transmission. And the factor that is measuring how worse is the signal-to-noise ratio is basically the ratio between the power of the modulating signal with modulation index A and 1 plus this power. Taking into account the relationship of this power with the power of the modulating signal through the modulation index A, the higher the modulation index, the better the performance. The lower the modulation index, the worse the performance. And finally, we have the vestigial sideband modulation. Now, the power of the signal term, the power of the noise term, the ratio can be written this way. We have 1/4 here, 1/4 here. That can be simplified. And now we want to write this expression as a function of N0 times B. Because of this, we include B here and here in the numerator and the denominator, and rearranging the terms, it's easy to see that we have PS divided N0 times B times this factor here, the ratio between the bandwidth in hertz of the modulating signal and this bandwidth plus the vestige. Therefore, this term is multiplying the value of the reference of the signal-to-noise ratio for a baseband transmission. Again, this factor is always lower than 1 because the denominator is higher than the numerator, and the conclusion is that also the vestigial sideband modulation has a signal-to-noise ratio that is worse than the signal-to-noise ratio in a baseband transmission. However, in most of the cases, this factor is lower than 1, but this is not, it is not so far away from 1 because usually the vestige is much lower than the bandwidth of the modulating signal. So it's worse than the baseband transmission, but relatively close to this signal-to-noise ratio.